Hello everyone. Today in this video we will talk about discrete time signals and systems. So in this chapter we will talk about a continuous signal, how do we convert it to a discrete signal, then how do we describe a discrete system that will process this discrete signal, and the output of this system will be a discrete signal. Then how do we convert it back to a continuous signal? So in today's video, we will talk about continuous to discrete signal, moving from here to here. And we will talk about different signal models like the unit steps, impulse, sinusoidal, exponential function. And next video, we will talk about signal operation, discrete time signal classification, and digital resampling. And in the third video, we will talk about discrete time systems and examples, and discrete time systems property. Okay, so let's move on to how do we convert from continuous signal to a discrete signal. Let's take this example. So we have a continuous signal that is just pure exponential, and we want to convert it to a discrete signal, something like this. The first step is you have to decide the sampling interval. How often do you take samples? Do you take it every 1 millisecond or every second? This will be determined by the sampling theorem. The sampling theorem says the following. You check the bandwidth of the signal, or sometimes the maximum frequency in the signal. Then the sampling rate should be equal or larger than twice the bandwidth or twice the maximum frequency in the signal. So for example, in speech, the maximum frequency in speech is 20,000 hertz. So the sampling rate should be 40,000 or more. Okay, so let's assume we decide to sample this continuous signal with a sampling interval 0.1, which is every 0.1 second I take a sample. So this is 0.1, this is 0.2, and so forth. So now since the time is discrete, since I'm taking every 0.1 second, x of nt, capital T is the sampling interval, is e minus nt. So basically I change t to nt, where capital T is the sampling interval. Now to represent a signal in a discrete form, usually we don't write it this way, we write it just x with a square bracket n, where n is the number of sample, like n is 3, that is the third sample. And we already know what's the sampling interval, which is 0.1 second. So if n is 3, it means in time, it's 3 times the sampling interval, 0.1, so that's 0.3 seconds. So from now on, that's how we're going to express the discrete signal. Okay, so x of n in this case will be e minus n 0.1. Now I can rewrite this as follow, e minus 0.1 to the power of n. Now you can use your calculator and calculate what is e to the power of minus 0.1, and you will find it to be 0.905 n. And that will be the discrete signal, which is this. When n is 0, x of 0 will be 1, which is this sample. When n is 1, then x1 will be just 0.905, which is this sample. When n is 2, that will be around 0.81, which is this sample. So this is sample 1, 2, 3. Okay, let's now look at the sinusoidal continuous signal. Now we have this sinusoidal signal, which is continuous, the blue curve. So I can write x of t as cosine omega t, where omega is radians per second. Also, I can replace omega by 2 pi f. So now x of t also can be expressed in this form. Now f is cycles per second or hertz. So for this signal, the frequency is 2. There is 2 cycles per second. So this is 1 second here. So there is 2 cycles. That is 1 cycle, 2 cycle. Since f is 2, the sampling rate, it needs to be twice that. So I can sample it at 4 samples per second. and then I can reconstruct the continuous signal back again from the samples exactly if I take 4 samples per second. But let's say I decided to sample it at 11 samples per second. So now the sampling interval t is 1 over the sampling rate. So that is 1 over 11. Now if I write the signal in the discrete form, I start with cosine omega t and I replace t by nt, where capital T is the sampling interval. So now I can rewrite x of n cosine omega and little t, now it will be tn. Now I can define this quantity here as the digital frequency. So cosine omega n, where this omega, I will call it the digital frequency. And later on, we will see its radians per samples. Or I can say cosine, that omega here is 2 pi f. So that will be 2 pi f tn. And I can write t as 1 over f of s, this. So now this will be cosine 2 pi f of s n. Now this quantity here, I will call it the digital frequency. So I can write it as cosine 2 pi f n, where that capital F is the digital frequency. And if I want to know what is the unit, well, f is little f, the analog frequency, over f of s. This little f, the unit is cycles per second. And the sampling rate f of s is samples per second. So this second will cancel here, and this will be just cycles per samples. And that's the unit for this digital frequency. So if I find the numerical value for f, it's little f, which is 2 Hertz, that's this one here, divided by f of s, the sampling rate, which is 11 here. So that means there are 2 cycles per 11 samples. Let's go back to the graph here. So we have 2 cycles per 11 samples. We said we will have 2 cycles up to this point. So let's see how many samples I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The digital frequency f is 2 cycles per 11 samples. Don't count this, because that will be the repetition of this sample. It's just going to repeat itself. Let's look now at this digital omega here. So we said omega is 2 pi f capital T, which is 2 pi f over f of s. Now this omega, the larger it can be, is when the sampling rate equal twice the frequency of the signal. Usually f of s is more than twice f, but the minimum f of s can be is twice. So then in this case, that will be 2 pi f over 2f, and that will be this cancel and this cancel, and this is pi. So pi, that is the maximum it can be. And this is very important to keep in your mind. The digital frequency, which is radians per samples, cannot be larger than pi. The only way for omega to be larger than pi, if the sampling rate is less than twice f. And if that is the case, then you undersampled and aliasing will happen. So this is important to keep in your mind. Omega equal or less than pi. Okay. And again here we said the unit for omega is radians per samples, and for the digital f is cycles per samples. Now if we sample under the Nyquist rate, then this what will happen. Let's look at this. Undersampling and aliasing. So if you have a signal like this one here, omega is 0.5 pi, which is less than pi. So there is no aliasing. That means that signal was sampled at the right sampling rate. And if I want to know what is the digital frequency, I can rewrite this as cosine 2 pi 1 over 4n plus theta. And that will be the frequency. F is 1 over 4. That means there is 1 cycle per 4 samples. So the sampling rate is 4 samples per cycle. But here we have a problem. Here omega equal 1.6 pi. This is larger than pi. So there is aliasing. So I can rewrite this as 2 pi 8 over 10. So the frequency in the analog signal is 8 Hertz, but I sampled at 10 samples per second. I should have sampled twice the 8, like 16 or more. So now there is aliasing. So that omega will not act as this big frequency. Actually, it will act as a lower frequency. Graphically, you can imagine it this way. If this is the allowed frequency in the digital signal, now you have 1.6, which is somewhere here. So this will be aliased, as we explained in the sampling theorem, as this signal. So this is 0.6 above pi. This should be 0.6 below pi. So that will be 0.4 pi. So 1.6 pi, you will hear it as 0.4 pi. Now we can find the apparent frequency this way or use this equation. This is when we did sampling theorem. How do we find the analog apparent frequency? It's similar here. This is the apparent frequency. This is the frequency you are trying to figure out, like in this case 1.6 pi. And this is modulo operation. And let's see how to use this equation to come up with the same answer here. So the apparent frequency equal absolute value. Omega is 1.6 pi plus pi modulo 2 pi minus pi. So this equal 2.6 pi modulo 2 pi minus pi. Now 2.6 pi divided by 2 pi is 1, and the remaining is 0.6 pi. So that will be 0.6 pi minus pi. And this is 0.4 pi, which is the same as here. So this signal, if you play it, it will sound like cosine 0.4 pi n plus theta. Okay, let's do this example here. So the apparent frequency will be absolute value, and this will be. And this equal 3.3 pi divided by 2 pi is 1, and the remaining is 1.3. So the answer will be 0.3 pi. So then this will appear as cosine 0.3 pi n plus theta. Now aliasing is something you probably experienced it in visual observation. For example, the wagon wheel effect. If you are driving by a car and you are looking at the wheel and it has rim, at certain speed, if the car is moving this direction, you will see the wheel spin this way. But as the car speed increased, suddenly you will start seeing the wheel spin in this way at very fast rate. But suddenly, as the speed increase, you start seeing the wheel spinning in this direction at a slower rate. So opposite. What happened is our visual system can sample at 30 to 40 frames per second. But as the car is going very fast, now the rim in the wheel is moving too fast for our visual system to sample it at the correct rate to see the motion correctly. So now it's aliased as a slow motion and in the opposite direction. This is the same if we look here. Imagine you have this stick and it's rotating at higher speed, like 280 degrees per millisecond. So it's moving this way. Then when it is here, it's moving this way 100, now it's here. And when it is here, it's moving 180 degrees per millisecond, now it's here. But now it's moving at a very fast rate. Our eyes actually will see it this way. It will see that stick moved here. the opposite direction. And when it is here, it starts moving this way. And when it is here, it starts moving this way. So now we are seeing the rim moving in this clockwise instead of counterclockwise. And at what speed it is moving? Well, if it was moving here at a speed 280 degrees per millisecond, that means x here is 100 degrees per millisecond because that pi is 180. So now we're going to see it's moving actually in this direction. At what speed? It will be pi minus x. So that will be 180 minus x, which is 100. So that's 80 degrees per millisecond. So that's how it will appear to us. It was here, then from here to here, then from here to here. Okay, let's look at now this exponential function. In signal system or in Laplace transform, we said x of t can be represented as a linear sum of this exponential function, where here x of si is the Laplace transform, and I can go from minus infinity to infinity. And esi, we said, is, here si, we call it the complex frequency. It consists of two parts, decay rate and oscillation rate. So S, it could be sigma plus j omega, where sigma is the decay rate and omega is oscillation rate. For example, if sigma is positive, then it will be growth. So the signal will look something like this. It has some oscillation, whatever omega is, and it has a growth. If sigma is negative, then the signal will look something like this, a decay. So let's see, how do we express this continuous exponential signal? So the first step is, if I want to convert it to a discrete, x of t, es of t. So now I will let t to be tn, where t is the sampling interval. So now the discrete signal x of n will be, now if s is complex, it will be, now I can express this signal e sigma tn times e j omega tn. Since sigma here is real, it could be positive or negative, this quantity here will be just a number. It could be 1.8, 2, 20, or 0.1, 0.2, 0.3. So we call this R, N. Now this omega t is the digital omega. So I can rewrite it as ej omega n. And I can write this as r e j omega to the power of n, and we will call this variable z. It's equivalent to the variable s in the Laplace domain. This will be the variable z in the z domain. So this will be Zn, and the magnitude of z is r, and the angle of z is omega. And again, depend on omega and sigma, x of n will have different shape. So let's look at these graphs. So x of n is this one. Now, if omega equals 0, there is no oscillation. Now, in this case, it's a decay. So r, or the magnitude of z, or e sigma t is the sampling interval, is less than 1. For this graph, again, no oscillation, so omega is 0, but z is 1. That means e sigma t is 1. So that means the only way for this to be true is sigma is 0. Then you will get these constant samples. When sigma is larger than 0, then e sigma t is larger than 1. So that is exponential growth. If you think of sigma as frequency, that is the growth rate. Now in this case, there is oscillation. So omega has some value. It does not equal 0. And it's decaying. That means the magnitude of z is less than 1. Here it oscillates, but it doesn't decay. That means the magnitude of z equal 1, or the same thing, sigma is 0. And omega does not equal 0 because there is some oscillation here. And in this graph, r is larger than 1, or it's the same thing you say the magnitude of z is larger than 1, or the same thing sigma is larger than 0, and it has oscillation. So that means omega does not equal 0. There is a frequency. So from this simple exponential function, depend on sigma, depend on omega, you can get any one of these 6 functions. Let me clean and clarify one more point. Now, when we said x of n equal Rn ej omega n, and we plotted these different graphs, we are plotting only the real part of this function, because this function is Rn cosine omega n plus j sine omega n. So we are only graphing the real part. So we are graphing xn, the real part of this. That's what we are graphing here, which is only this component. So now let's move on to the next slide to link Laplace and the Z transform that we will be learning soon. If I look at this exponential signal, which is the real of ESIT, and here S, let's assume this complex frequency is this one. So sigma equal -3 and omega equal 2 pi 6. Now if I plot this frequency in the S plane, let's call this -3 and here 2 pi 6. So that would be the frequency. Now, if I sample this signal to get the discrete signal with sampling rate f of s16, then z will be e sigma t e j omega t. And sigma is -3, and the sampling interval is 1 over 16. So that will be -3 over 16. ej 2 pi, omega here is 2 pi 6. And that sampling interval t is 1 over 16, 1 over the sampling rate. If you use your calculator to find this, you will find it 0.83 ej 3 pi over 4. So that is z. If I plot this z in the z plane here, it is a vector with this angle 3 pi over 4, which is this, and a length that is 0.83, which is this one here. This unit circle is 1, so that's 0.83. So this point is mapped to here, from the S plane to the Z plane. Now, if I have a continuous signal, like speech, with frequency f range from 0 to 20,000 hertz. So omega then will range from 0 to 2 pi 20,000 hertz. Now, if I sample this continuous signal at the Nyquist rate, which is 40,000 per second, then the digital omega will range from 0 to 2 pi 20,000 divided by 40,000, you get pi. So if this omega, the minimum is 0, in the S plane will be here. So this is omega equals 0, and let's call this point here, omega is the maximum for the speech, it's 2 pi 20,000. Now this range of frequency will map along this plane here, along these points, where this 0 will be omega 0, which is here, that's omega 0, and the maximum here will be pi, and that will be mapped here, pi. Any frequency in these points here will be either here or here or here or here, and so forth. This we will come back to it again when we do the Z transform. Okay, let's now move to an example that shows the impact of aliasing. Consider the discrete time exponential, which is the real of Zn, obtained from sampling the signal, which is the real of this signal est, with a sampling interval t1. Now, using Z equal es capital T, plot Zn as well as EST for reference in this interval for n larger than -5 and less than 5. For the cases s equal minus -0.1 and s equal minus -0.1 plus j pi of 2. And comment on the result. Okay, so let's solve this problem. First, we have the continuous signal. So let's call it x of t. And we are taking only the real part. And if I sample it to find x of n, it will be E S capital T n. Now they said the sampling interval is 1. So that means xn equal ESN. Now they said consider first s equal minus 0.1. So for s equal minus 0.1, x of t will be, and x of n will be. Now if I plot these, that's the curve I will get, the solid line. If I plot this digital signal for different value of n, when n is 0, I get the 1 here. When n is 1, I will get this value and this and this and this and this and so forth. When n is a negative value, I get these values. Now let's consider the second case. When s equal minus 0.1 plus j2 pi, then x of t will be, let's clean up these. Now if I take the real part, then x of t will be. Now to find the discrete signal with this sampling interval, then x of n will be, and for t equal 1, that will be, if I use the computer to plot these for n in this range, then I will get these points here, which is the same as this point here. I will be missing the oscillation here. So when I look at the sample x of n of this one and x of n of this one, they are exactly the same. It seems like plotting these and these, and cosine has no impact, because no matter what is n is 1, cosine 2 pi is 1. N is 0, cosine 0 is 1. N is 2, cosine 2 pi times 2, that's 4 pi, cosine 4 pi is 1. So this will always be 1. So really, these two signals are the same. And that's why the plots came out the same. Now, do you know why is that the case? Because here is why. Omega equal 2 pi f. And omega for this signal is 2 pi. So that's 2 pi equal 2 pi f. So f is 1. So for this sinusoidal, the frequency is 1. So the sampling rate should be twice the frequency. So the sampling rate f of s should have been 2 samples per second. And the sampling interval should have been 1 over 2. That's 0.5. So that's the problem. We are sampling at a rate 1 sample per second. So here fs is 1, which is below the Nyquist rate. And that's what happened, aliasing happened. So what do we mean by aliasing? Here is what we mean. For the x of n discrete signal, the digital frequency omega is 2 pi. So the apparent frequency will be the frequency here 2 pi plus pi module 2 pi minus pi. And this will be, and 3 pi module 2 pi, it's 1 and the remaining is pi. So this will be pi minus pi, that's 0. So the apparent frequency will be 0. So that will be the same as cosine 0n, which is just 1. So omega 2 pi, because of the undersampling, it will appear as a DC. And that's why this will be 1, no matter what is n, because of aliasing. And these two signals came out to be the same. to move from the continuous to the discrete, it's very important to take the right sampling rate, which is above the Nyquist rate. Okay, let's move on now to another type of signals, which is the unit step function. The unit step function, u of n, it's equal 1 for n equals 0 or larger. So if I plot it, it will be these plots, 1, 1, 1 forever. And for n less than 0, it will be just 0. And if I plot u of n minus u of n minus 10, later on we will find out u of n minus 10, it's a unit step function that is shifted 10 units to the right. So this plot will be something like this. So that's u of n. And if I plot this, it will be a unit step function that started at 10. So when I subtract this signal from this signal, all these samples will cancel. The only samples that will survive is all these samples up to the 9th sample, because this is all zeros up to the 9th. So this will cancel and this will survive, and that will be this unit pulse function. And we will see different application of a unit pulse function. The next function, very popular one, is the discrete time unit impulse function, delta n. So that delta n, it's a sample at n0. So it equals 1 when n equals 0. And if I have delta n minus 2, that will be a unit impulse function located at 2. Basically, you set the argument of delta to equal 0. So n minus 2 equals 0. So n equal 2. So that's the location of this impulse. Now, impulse, we use it in sampling. So if I have a signal, let's call it x of n, and I multiply it by this impulse. So this signal x of n could be something like this. And let's say this is m here. So now if I multiply this signal by an impulse located at m could be 4 or 7, and let's say this amplitude here is 4, and this is m, then everything here is 0. So when I multiply this by this, the only sample will survive is these samples. So I will get a delta function, which is this one, and the amplitude of it will be this amplitude, which is x of m, and that's what we get. Now there is a relationship between delta n and u of n. In the continuous case, the integral of delta t dt, we get 1. Now in the discrete case, integration become a summation, and then I will have here delta m. Now to evaluate this summation, how do we evaluate it? If, for example, I want to know what is u of n, let's say at n equal 2. So what is it equal? Then here there will be 2. And then I will sum a delta function at m minus infinity all the way to 2. Well, that delta function equal always 0 until its argument, that means until m is 0. And m equals 0, it's in this limit. So I will get 1. If I want to find the unit step at, let's say, minus 1, then n here is minus 1. And the argument here, m will go from minus infinity to minus 1. So it will never be 0. So you will always get zeros. So for negative, you get 0. And this will always be 1 for a positive n. And that's basically the unit step function. Now, derivative of u of n. In the discrete case, du of t dt equal an impulse. Now let's look at the discrete case. Well, if I have u of n, then it is this. So if I want to take the derivative of this one, derivative, if you remember, if you have like a signal like this, and I want to take the derivative of this signal, I take a sample here minus this sample. Let's say this is x3 minus the adjacent sample x2. divided by the interval here, t. Well, the same thing here. The derivative of u of n, if I take this value minus this value, I get 0. Derivative at this instant of time, it's this value minus this value. 1 minus 1 is 0. The only value you will get is at n equals 0, because it's this value minus this value, that's 1, divided by this interval, which is 1, so I get value 1 here, and that's just delta n, and everything here will be 0. So the derivative of u of n, you get delta n, and you can think of it as u of n, subtract from it u of n shifted 1 unit to the right. So if that is u of n, then u of n minus 1 will be this one. If I subtract these from here, the only thing will survive this impulse, which is a delta function. Okay, let's look at this example. Describe the signal x of n shown below by a single expression, a mathematical expression, valid for all n, comprised of unit impulse and step function. So they want us to express x of n using a unit step function and a delta function. Well, there are different solutions for this problem. One way I can think of it is this way. I can think of this portion here as a ramp of a slope 1, because height is 4 divided by the base is 4. So then I can say this is x of n equal n. When this is 1, 2, 3, when n is 1, it is 1. When n is 2, it is 2. When n is 3, it is 3. But this only valid in this interval, not valid in this interval, not valid here. So then I have to multiply it by a window of these sides. So then this will be u of n minus, I need to create a window that consists of 1, 2, 3, 4. So only multiply this by this window. But then here everything is 0. So if I have n to continue up here, it will be multiplied by all the 0, so they will not exist. To generate this window, I can do it this way. It consists of u of n, and I need to subtract from it another unit step function, but it starts at 5. So this will be a unit step function delayed 5 units. So when I subtract this from this one here will be subtracted from here, you get 0. The next one here will subtract it from here, you get 0. So I will end up only with this, which is this. So then to get this one, it's u of n minus u of n minus 5. So now I got so far this portion of the signal. Now I need to get this portion. Well, this portion looks like a unit pulse that starts at 5 and end at 10, except this one, it doesn't equal 4, it's equal 2. So let's assume it's equal 4, and let me generate this. Then I will subtract this portion from the whatever signal this is equal. So then I can say plus a unit step function that starts at 5 minus a unit step function that starts at 11. And these will have amplitude 1, but this one, they have amplitude 4. So I'm going to multiply it by 4. Now, as I said before, this sample here, it's size 2. And its location is that 6, 7, 8, 9, 10. So its location at 8. And it's only of size 2, not of size 4. So now I have to subtract an impulse at this location, and I have to subtract 2 units of it. So that's minus 2. So the signal is well, this ends this video for this topic. Next video, we will talk about signal operations, which is time shifting, time reversal, time compression, time expansion. This will be the topic of the next video. Thank you for watching, and see you soon.